Okay, so it works? Fine, wonderful. Okay, so welcome to my talk on testing theories beyond general relativity. That's the idea for today, and the contents are in a bit is that we want to first explore how, like, also written in the abstract and the official title, is that how black holes work, what is the physics of black holes, and how do black holes fit within this framework of GR. And secondly, in a way, and that's a bit the main objective of today, is to understand how can black holes be really used to test new theories in the standard model? Like, how can we really find out whether new theories of gravity, especially of quantum gravity, be verified, and how can we understand if they are true to a certain degree? And for this, we will be looking at a specific theory of gravity also called holographic duality. That is something proposed within the framework of something known as superstring theory and supergravity. Although we will try to remain as informal here as possible. So the idea is really in this section to not stress too much on, I would say, mathematical rigor, but more on, in a way, physical intuition, and to understand what's really going on in the theory of gravity. And in the last section of this presentation, we are really interested in understanding how can we really utilize gravitational waves to test theories of GR, and how, because we can do that by now, and that is something which is most likely going to be instrumental to understanding how this world really works. Okay, but first of all, I would like to begin at the beginning of all time, which is in 1914, when Einstein proposed his famous equivalence principle, which is the beginning of GR. And really, this is very important, so I'll begin from there, is because from this statement, if you will, we can deduce more or less the entirety of what GR really forms as a theory. So it states in the end that any object can be understood locally to be falling in a free-falling laboratory system. So very locally speaking, gravity is very like forms straight lines, like straight field lines, and globally speaking, that just means that in order for this locally to be straight, we would need globally for space to be deformed by gravity. So in a way, you can understand that space forms to kind of make sure that gravity is nullified. So if you have an object which is a sphere and it is very massive, then the space curves the other way around. So again, we have this straight line picture, locally speaking. And that means in the end that gravity is something which deforms and curves space-time as such. Also, and that's something which also follows from there, is a second thing which I have not written here, but is something which I can just say here, is because we know that the velocity of light is something which is constant in all inertial frames. It's something which is set in the framework of special relativity. What we see from that is that since this is supposed to be true, that light is also bent by gravity. So because locally speaking, we have an inertial frame which again follows the Einstein equivalence principle, and since any local frame is equivalent to a Newton laboratory frame, we can from then deduce that also light needs to be bent. Okay, that is the basic, and now how do we really move on from here? Well, we move on from here by introducing something called the Einstein field equations. This is equation 1 here, and we will encounter this a couple times in this talk, but then basically it's really about understanding that this principle in here can be really written in a way formally in an equation, because if we really say that we have matter, which is given by this very complicated object called T mu nu over here, as the matter distribution of the so-called stress energy tensor, that's the one side of the story. This is just the mass, if you will, the energy of our theory. And on the left-hand side, R mu nu is the curvature of the geometrical curvature of space-time. What it just means is very simply is that, and that is how you can really equate and understand this equation, is it equates to geometry equals the matter distribution. So the geometry of space-time is equal to the matter distribution of the universe. And secondly, that's the other thing, is when they kind of did their measurements, they found that, okay, well, maybe we need to modify our theory a little more, and that's when this lambda, the cosmological constant, comes into the picture, or plays here into, is that this is really about, if you will, the acceleration of our universe and how fast this universe kind of gets bigger or inflates, better said. So the whole theory of how our universe really worked, in a way, is in a way written in this very, very, I would say, dramatic equation. And to be fair, this looks even very simplified, if you will, but R mu nu is a so-called tensor. It is a matrix with 10 free entries, and that means we have a huge system of 10 coupled partial differential equations, which we have to then solve. And that is, I think, pretty difficult, and people struggle with that until today. So most solutions we actually have to this are either in the linear regime, which I'll get to in a sec, and also numerically, which is the most easy way, depending on the boundary conditions that we look at. Okay, so at the second thing also, you can ask questions anytime before I forget that, if anything is unclear. But yes, that's the most important equation, is saying geometry of spacetime is the same as the matter distribution of a universe. Okay, now in the next step, what we're interested in is saying what really is the solution of this Einstein field equation. And the solution of the Einstein field equation are metrics. So what really instead of like, usually we have an equation which is dealing on scalar functions. In this case, the solution of the Einstein field equation is the metric itself, which kind of puts things on kind of upside down, turns things upside down, because before that we kind of assume the metric of spacetime is something invariant, something which we impose on spacetime. We want to know how to measure a length, and that is just fixed by some physical intuition of sorts. Like if we take a meter scale or something, we know this is a meter regardless of how the sun is changing its position. But GR kind of contradicts or says this is wrong, because actually the way we measure spacetime, the way we measure time and distances is dependent on the matter distribution of a universe. So depending on how exactly the sun's masses or the sun's mass changes, for example, which is a very minor effect also. So, but for example, or if a black hole collides with a supernova or something which changes the matter distribution of the universe in some way, or galaxy collisions, then what happens is that the metric or the way, 1 meter that was earlier considered to be 1 meter is no longer 1 meter, but a different length, because the scale of our universe changes, and that is the point. And this also means that GR is in the end, effectively, and that's how you can summarize the whole theory of GR, a theory that tells us how distances and times are measured. Okay, now the next step is analyzing solutions of general relativity. And a very, very dramatic and catastrophic solution of GR is this black hole solution, something which was very long disputed to be a reality, but then we know it's no longer because there are lots of pictures and other evidence for this. So what it really says is black holes are a solution of this, very fundamentally a solution of this Einstein field equation too, which effectively admits a so-called singularity feature, meaning for some reason or the other we have observers entering a certain region of space-time and are no longer able to escape. This is called a singularity and a horizon feature. And we will now, in a sec, explain exactly what this means, but if you will, you can understand a horizon as a space-time boundary that separates, in a will, the interior and the exterior causally. So if I'm inside the interior or the horizon, I have no longer a connection to the exterior causally, because there's no way I can actually escape without moving fast in the speed of light, which is kind of the effectiveness of saying that something is causally disconnected. Okay, so what exactly does this mean? Well, these black holes are a solution that admit the singularity, and we define the horizon as, if you will, a space-like curve that a conserved vector field, which is a very specific energy, there's an energy vector field known as time. There is an angular momentum vector field known as, or a rotational vector field known as angular momentum. These are all conserved vector fields depending on the symmetries of space-time. And what we say is that such a vector field, if it's time-like, so there's a causal connection if it propagates from point A to point B, if A and B are causally connected, meaning you can go from A to B without being faster than the speed of light, then you say A and B are causally connected, so-called time-like vectors. And if you cross this boundary, then any time-like vector becomes space-like. So if point A is outside the horizon and point B is inside the horizon, then the line that would connect them, or the trajectory, would have to be a space-like vector, and that defines the boundary. More specifically, you can actually find also differentiability criteria on this horizon, in the sense that you can show that at the horizon boundary, your curves are no longer C1, but no longer really, at the point we have a discontinuity of sorts in the differential in the first derivative, and that makes sure that we have this change from space time-like to space-like vectors. Okay, and the second definition I want to look at is a singularity. A singularity is a space-time point X, such that no geodesic can be smoothly extended to that point. A geodesic is a solution, if you will, physically speaking, any points. If an observer moves from point A to point B, he will move along physically the shortest line, dependent on the scale we just introduced over the Einstein field equation. So we have a scale, and with respect to that scale, we want to move as fast as the shortest distance possible from A to B physically, if no other forces are acting on that thing. And formally, mathematically speaking, it means that this geodesics, there does not exist a way you can go over a singularity just like and extend it over a singularity. And this is not possible, otherwise this would not be a singularity, because then we would be able to just cross over it. And so a real singularity is one which it's impossible, regardless of the change or the choice of your coordinates, it is impossible to enter that coordinate frame. All right. So far, any questions? Does this all make sense so far? Yes. Okay. Geodesic is a very fancy way for between points A and points B, the shortest distance, if you will. So, for example, on a plane, the shortest distance is a straight line connecting 2 points. That's the shortest distance. You could go like this, but that's all going to be longer. On a sphere, it's all, when you look at aeroplanes, they sometimes go these lines here. These are great circles, they're called, and that's the shortest line on a curve, because if you go back, if you kind of project your sphere onto a plane, then that'll be a straight line, and you want to kind of tie that up onto your sphere. Okay, does that make sense? It's just the shortest line, and that's the physical intuition. Meaning, an observer is someone who moves on geodesics, because you cannot observe anything, also classically speaking, or from the point of Newtonian mechanics, if forces act on you. So otherwise you will just move without any forces acting on you on a straight line in a plane. Otherwise you would have forces. Okay, and now just for fun, this is this famous picture of a black hole, which was found in 2019 and also earned the Nobel Prize at that point. I think also most notably to Roger Penrose, who proposed that GR in his whole life is evident that black holes are a consistent prediction of GR, not just some theoretical makeup of something. They really exist, and we also believe that, for example, black holes are the reason why our galaxies are formed that way, because because in the center of our galaxies we believe to be some sort of supermassive black hole that, due to its gravitational attraction, is able to kind of keep the galaxy clusters together. And so black holes are, in a way, also by now theoretically very important to understand how the universe is existing and how galaxies forms and all the like. So they're actually now very, very robust predictions of GR. Okay. Yes, and that kind of puts me at the last part of my theoretical introduction, namely gravitational waves. So what are gravitational waves? So we go back to this Einstein field equation. We've seen it the third time, so I can give it a new number. And gravitational waves are, in a way, perturbative expansion. So assume that we have already a solution of our gravitational waves, so of our field equations. We have a solution called g mu nu. We have this already. And now we're interested in, so assuming we have something like, we have the sun has some small interaction with another object, in principle, or smaller object. It's not very massive. And so we really don't believe that there's going to be a very big change in the space-time metric. It would be rather weird if small interactions would drastically alter the way space-time is curved and how it works. So instead what we do is we are actually interested in understanding, what do small changes do? And what you can do is actually, for example, if eta mu nu would be like the Minkowski metric, the very typical S metric, a very plane metric, and then we are interested in small perturbations around a solution we know. Then this h mu nu, and this is like a small one, then what actually happens is this h mu nu obeys a wave equation. And gravitational waves are in the end nothing else than ripples of space-time, or as I would call it, or better said, gravitational waves are small ripples in the way we see length, are waves of the metric itself. And that is a very, very, I think, interesting prediction to say that actually the way how length and curvature is something which is subjected to a wave equation, a constant wave equation which always slightly ripples space-time itself. And this is something which also been measured, of course, and again in 2016, that's a very famous prediction, was in the end also found and awarded also a Nobel Prize for it, with this LIGO experiment, which used lasers to actually detect these very minimal changes because they're extremely minimal, they're very difficult to detect, and so it was very hard until recently to actually find a proper experiment doing this. And they did this via a minutious composition of different lasing system and interferometry that yielded, if you will, the small diffraction patterns that changed. They could measure those, and that was, if you will, the reason how they found gravitational waves. And then there are other things like Virgo, which also do the same thing, but also try to predict for astrophysical black holes now, this is a bit more difficult because they're smaller in size. What if also there we can measure gravitational waves and their ripples and their magnitudes? Okay, does this make sense? Because that will get important later, and so it would be great. All right. Then lastly, let us address two things still. First of all, what emits gravitational waves? So as I said before, nearly everything does. So really, you can think about it like this. Nearly everything in this world emits gravitational waves because in the universe, nothing is really stationary. And so every time something changes, for example, you have a supernova, you have a pulsar, you have some very densely rotating system of neutron stars or something like that, then all these things will emit gravitational waves because of course, from the proportion in comparison to the rest of the universe, like from the mass distribution, they're very, very little and very small and very insignificant. But because they're so insignificant in comparison to the whole universe metric, they will emit, if you will, linear regime gravitational waves, especially when we then again detect those. And so this is something which is ubiquitous in the whole system of the universe, and actually can also be used now. We are thinking of new ways of using gravitational waves, for example, something called gravitational lensing. So, as I mentioned before in my introduction, is that light is bent by gravitational wave, or by gravitation, because of the curvature it has to go back. So, what we actually do, something called gravitational lensing, it is called, and gravitational lensing is about actually, if you will, understanding how also gravitational waves are deformed by the trajectory of space-time itself. And so we can also maybe understand how massive stars are, how massive black holes are, just from that. From how much they're bent, how much they're curved. Oh, and I see this is a very bad typo. I have kind of latex, but never mind. All right. And now again, what I said before is, of course, you have problems measuring these bigger systems, but yes. All right, and now the last thing I want to actually allude to is, okay, so first of all, we know, and I say all of this because we know all of this is true. We've measured black holes, we've photographed black holes, we've measured gravitational waves, we've done all of this. And so the question is, if GR is such a well-predicted theory, if everything works as it should, why are we looking for something new? And in a way, that's the starting point of the whole conversation we're going to have is, why are we doing this? And the reason is there was something called the cosmological constant problem. And that was something before. We tried to really measure how much does the universe accelerate? Like how much, what is the, and GR we measured, we can kind of we assume the universe is more or less homogeneous because probability is kind of low, it's not. And from there you can kind of assess how much matter is in the universe. And from there you can kind of go back to this equation here and check, okay, what is this cosmological constant? We can kind of see what, we give homogeneity, we give isotropy, and all these things inside. What is the cosmological constant? Kind of go back. We kind of go back and use the metric we have and try to understand, okay, what would have to be the cosmological constant for us to understand all of this? Well, they did their calculation and they came to something about the order of 10 to the power 1, if I remember. And the problem was, however, then they actually measured it with the Hubble telescope. You can kind of see that if it expands, then you send light out, you have like reflected back, you have something called a Doppler effect. So because the things are moving, the universe is kind of moving, then you can see that going back and forth will give you a redshift. And you can measure this redshift because you can, again, kind of get back the light. And what they measured is from that is that the cosmological constant would have, the error that they had was about the order of 10 to the power 120. And that is a pretty big number. And so GR was effectively not able to predict this. They predicted it from GR, and there has to be something wrong, and this has been confirmed by many consecutive measurements. So there has to be something wrong with our understanding of this world. And now we get into something which I think many people maybe have heard of. It's something called dark matter, dark energy, all these buzzwords. And that was the reason it was introduced. They didn't understand why the universe is accelerating this much, why the universe is getting at that scale. And so they introduced dark energy. And that's the reason, and dark matter. And we don't know what dark matter is because we call it dark matter, because there's no idea what it is. And so the other way of approaching this is, of course, maybe the theory of GR as we know it is wrong. And that maybe it works in these big regimes, like always in physics. Quantum mechanics also works, is something in small regimes, and we have big regimes where, well, like classical mechanics does a great job in predicting the world. And again, here we think, okay, maybe GR is just a theory that gives us very good results at the larger scales, but in the precise interaction of matter in this smaller scale regime, that there must be a theory of quantum gravity which we are yet to understand. And that is something which we now will not do, but we will try to delineate. We will try to delineate maybe what ideas were in this region. But yeah, so far, any questions to this? Yes?
Which direction is the discrepancy?
It's much like the cosmological is much larger than measured, much larger. Any other questions? I'm happy to hold any questions. Okay, fine. Now, okay, the next step is, okay, so what can we do from this point onwards? Well, we are trying to find a new theory of gravity. And there are two possible candidates for this, actually, by now. And people say we've lost a lot of time, but in some way they're right. And the candidates that we have for this is something called string theory and loop quantum gravity. And loop quantum gravity is a very new theory and a very more difficult to write and formalize because it's been around for 10 years, maybe 15 years, as maybe something which is not similar to string theory, but a completely new idea. And then we have string theory itself, which is something also often kind of talked about. And string theory is something we will also kind of get into a little bit now, because we are interested in a way to kind of merge the same way we merged in a way special relativity and quantum mechanics to quantum field theory, so a relativistic theory of quantum mechanics. As quantum field theory, we introduced these fields and the second quantization, which is something I will not go into today, but we are interested, in doing the same thing. So we want to merge these theories and kind of now replace special relativity with general relativity, quantum mechanics with quantum field theory, and find a theory of quantum gravity. That is the main objective. So as I would see in this picture now, is you have this quantum field theory, and doing this is the question. And for this, we introduced something new. And this new thing is something known as string theory. Okay, so now in the remaining of my talk, I'm going to quickly give you an idea what is string theory about, why did we introduce this, what problem does it actually solve, and can we actually then in the end find a test of this theory. Okay, what does string theory do? Well, particle physicists are people who look for particles. And as they do, well, they try to understand everything in terms of particles. And when we kind of found particles for everything else, be it the gluon for the strong force, be it the photon for the electromagnetic force, we tried to produce a new particle, in this case the graviton, so as to fit our demands to physics. And the idea is now the following. Okay, so quantum mechanics and quantum field theory is all about finding a theory which is renormalizable or, in a way, physically acceptable. That means, in the end, you have to usually subtract infinity and divergences always. By subtracting divergences, you have to make sure that your theory becomes something real or a real value, and that subtracting divergences is not equivalent to just doing shit. So what we can think from this is the following, is that in gravity, the reason why a theory was not found so far, or was not done at that point with points, is that at each step you would have to subtract an infinite amount of infinities. And so clever people thought, okay, if we have an infinite point of infinities, then we have some problem of discontinuity along a line. The same way as the power set of the natural numbers is somehow the real numbers. They thought, okay, let's just replace these points which you're subtracting with a line. And that is the birth of string theory. If you will, at the heart of all particles, we have a string. And this string comes, if you will, however, with a few strings attached. And we kind of are interested in seeing, okay, so what is the dynamics of this new object? So what we can see is the following. So we distinguish now in this new string theory, this new approach, between open and closed strings. An open string is one which is kind of open, it's an open line, and a closed string is one which forms a loop. So what one found when one did the math of string theory, it's beautiful. One found that, okay, in the open string modes, we find directly the photon. That's the first excitation mode of the string. It's like a violin string which we excite, and we found a photon. In the closed string mode, the first mode we found was a graviton. It actually satisfied all the Einstein field equations, everything was nice, degrees of freedom were nice, everything worked out, and people were very excited about this. Because suddenly we had a theory of quantum gravity at our hand, or a theory of everything, better said. However, there comes a few problems with this. The first problem is that we have 26 dimensions attached to the normal string theory. If we try to find a quantum mechanically relativistic theory which satisfies the string conditions, we read 26 dimensions. That kind of put problems, because 26 dimensions are a few more than we have in our world, at least as far as we believe there are. So what do we do now? Well, in the next step, we try to find the so-called action principle. I know this is maybe a bit far-reaching, but in the end, everything in physics is derivable from, or at least we hope, is derivable from some kind of action principle. The action in this case is a bit more complicated. It's called the Polyakov action. And what it does is we now try to impose new constraints on our theory. How can we reduce the number of degrees of freedom and the dimensions to something which is more physically sensible? And this is, of course, complicated, but what it does is effectively, we can see like this, we have a few components in this metric. It's like a wave, if you will, or kinetic energy. However, coupled to a curly G mu nu, which is the background metric of the world. It's you could say our world has background Minkowski space, so if you will, a plane world, if you want to. That would be the big G. You have a string living in a background world coupled to its own metric, which is G alpha beta, which is, if you will, if a string moves in time. So if a point moves in time, you can see a line of the trajectory, right? I mean, if you would plot the trajectory of a point, it's a line. If you plot the trajectory of a line, what do you get? Does anybody want to say? A plane. Yes, a plane. And that's called, whereas the point line was called the world line, the new plane is called the world sheet. And so the G alpha beta is then called as if you will, the metric or the curvature of the metric of your world sheet. And there are much more extensions. I mean, if you have that already, what you can do the world cube so then you can extend this theory, of course, arbitrarily, but we won't. The thing however, which is the most interesting is the following. Now, where do we move forward? We try to reduce the number of degrees of freedom to something more sensible. We came from 26. Well, we recall in this world there are two kinds of particles, bosons and fermions. And so we were interested in finding, okay, can we actually first of all, find a symmetry in this action that allows us, because symmetries are good because they reduce degrees of freedom, first of all. Because they're symmetries, then they have to obey the symmetries, and we get equations for these symmetries, and then you reduce degrees of freedom. And secondly, can we use the constraints of the world to reduce the number of freedoms? And yes, one approach is called supersymmetry. That's something which just means that we use the constraint that fermions are antisymmetric particles. You exchange them, and you get a minus sign. We have bosons, which are symmetric particles, and that gives you a constraint on the particles itself. And secondly, well, scale invariance. You can look at this action, and you can see from your eye that this must be invariant under Mobius transformations. This is evident. No, it's not. But it's something which you can check effectively. It's a tedious calculation. It takes a bit of time, but you can do it if you want to. And what it just means is scale invariance means that a Mobius transformation or a generalized Mobius transformation is just a very combination of rotations and scalings. And they are also known as the automorphisms from the sphere out to the plane, but that's all fine. I'm just saying is that this theory is invariant under rotations and scale lengths, which is something called as conformal invariance. And so string theory gives rise, and this Polyakov action gives rise to a conformal field theory. So, or if you will, we can understand string theory in form of a conformal field theory. And that is something, okay. This gives us a rise to something which is a new theory of everything. And now what we are interested in is, okay, so what is happening now? We know it is scale invariant. We know this theory has to obey the constraints that fermions and bosons have. Then, well, what we try now is the following, is we define what's called supergravity. Supergravity obeys the constraints that fermions have. So we have it's antisymmetric under permutations of fermions. It is symmetric under permutations of bosons, so it's symmetric and it obeys these ideas. And secondly, well, it has a nice background. So when we reinsert all of these things into it and make it consistent with GR, we find that, well, in order to kind of balance out everything, it needs to live on a background with negative cosmological constant. And that is bad because we live in a positive cosmological constant. So that is bad. But it is the fact, and this is something which and so I will just give the definition. We have a space with a negative cosmological called anti-de Sitter space. It's named after a man called Willem de Sitter, who also lent his name to the second definition, namely the positive cosmological constant, which is called a de Sitter space. And so just to give a reality check, so if we have an anti-de Sitter space background, so that means that physicists try to find a way back. And they try to find a way back from this supergravity living on a negative cosmological constant, everything, to our world, which is a positive cosmological constant. So very complicated, but they found a theoretical solution at least, which is called the ADS-CFT correspondence. What does this say? Well, we recall string theory is a conformal theory, invariant under scales and rotations. We search a representant on our world, which is conformally invariant. So we look for a field theory, not a string theory, a field theory, something we know already, that is conformally invariant and respects our symmetries of fermions and bosons, such that we can omit string theory and omit supergravity on this weird background, which is effectively a very complicated background, to come back to our world, which kind of has a CFT, a conformal field theory living on it, which is the effective gravity theory of our world. And that is something we call ADS-CFT correspondence, or also, one sec, I'll just get holographic duality. Before that, let me just 1 second go a bit into the anti-de Sitter space geometry, just because I will use it in a sec, is that anti-de Sitter spaces can be understood. There's something called the Killing-Hopf theorem, and that tells us that the geometry of anti-de Sitter space is locally something like the sphere. If a sphere across the whole our d minus one dimensional plane. That's a d-dimensional anti-de Sitter space. That is, of course, complicated, and if you will, what it also means is the anti-de Sitter spaces have the thing is like that their time is a compact thing. So time runs in a loop the whole time, from 0 to 2 pi and goes back. So although a cosmological constant, as I said at the beginning, is something which refers to the acceleration of the universe, so if it's negative, you would assume it shrinks, or at least slows down, and kind of at some point there will be a point where it kind of all comes together. That's not necessarily the case because the space itself is infinitely large. So in contrast to a de Sitter space where we have a compact space and an infinite time, the reverse happens here. We have an infinite space and a compact time, so the idea of it shrinking is not necessarily correct because infinity can't really shrink together. It's a plane, and a plane you can't really contract to a point very well. So that's kind of the idea of it, is that it is a very difficult space to understand, and so it is a background which has, as you will, some strings attached to it. And now what happened is the following. This is all very complicated and difficult to see. So in 1997, a man called Maldacena, who also did a Pauli lecture a couple of weeks ago, proposed the ADS-CFT duality. This is kind of his. It's also called the Maldacena duality, actually. And he understood the following, is that the geometry of ADS space is something like SO2,4. SO1,3 is the Lorentz group with 1 negative and 3 positive indices. Now SO2,4 is the same, only with 2 negative and 4 positive indices. And ADS5, sorry, that's a 5-dimensional ADS space. And what he understood is, well, that is the same group as the local covering group of the conformal scaling group. That's very difficult to say, but in the sense what he said is that the ADS space and the conformal group, the conformal scalings, that is the same symmetry. So conformal invariance is the same as a symmetry group of anti-de Sitter spaces. And that makes the connection between ADS spaces and conformal field theories, namely that they have the same symmetry group. So what does he do? Well, we now relate a higher dimensional space, namely ADS5, if you will, a higher dimensional, 5-dimensional space, to our world, which is 4-dimensional, 1 time dimension, 3 spatial dimensions, via a 4-dimensional conformal field theory on its boundary. This 4-dimensional conformal field theory is, if you will, known also as S-duality, and we replace all these very weakly coupled interactions in this 5-dimensional space where we really can't work with because we don't have any ways of detecting it. We replace those with our conformal field theory on the boundary, and what does that really mean is that we found, or Maldacena found, a specific conformal field theory which is dual to ADS, crossed with the 5-dimensional torus. But ADS. And this ADS means, what does it really mean is that this conformal field theory is also called as super quantum chromodynamics, n equals 4 super Young-Mills. But in any case, we found one. Maldacena found a specific conformal field theory which gives us, it highlights this holographic duality specifically, One sec. Okay. And so we were actually very good so far. Next step is, yes, and what I said, we have this ADS5 cross S5, and he said we have a supersymmetric version of chromodynamics of strongly coupled particles. Chromodynamics is a theory of strongly coupled, strong interactions, so strongly coupled particles, which should then, so if something very weakly coupled happens inside the space, the outside boundary emits a much stronger back reaction to that. And so, if you will, what happens in the higher dimensional space in a weak way is strong in our world. So we could measure that actually. And that's exciting about it, because now that would mean that supergravity is actually something which can be reduced to our world via a different interaction, namely a very strongly coupled back reaction of particles living in 4 dimensions versus 5 dimensions, where we would not be able to detect such particles. Okay, so I didn't really give time for questions so far. Is there any questions so far? It is all hard, I know. But even then, be courageous. This theory is, so since this theory is conformally invariant and also supersymmetric, we had an amazing hopes for this theory. We had amazing hopes that this would actually work. And what is another thing? Well, just let me allude. Remember the cosmological constant problem from earlier, this thing that the world is accelerating much faster than we know of it. It's much faster than we would have measured it so far. Supersymmetry actually predicts the correct cosmological constant. So that is an exciting thing, that we know that supersymmetry does predict something which we know is correct. However, one has never found so far any supersymmetric particles. But maybe we will, or maybe we won't. But that is, of course, the problem with this. But if you will, the problem is, again, however, that we so far a graviton, or something which string theory tries to propose, this elementary particle which defines the interaction of gravitation itself, like the photon defines electromagnetic interaction, was also not detectable from like CERN or something like that. So the idea is now, okay, can we actually use black holes, which are very extreme gravitational objects, to find a new theory or understand if a theory is correct? Because it might be possible that the black holes, which are very extreme gravitational objects, satisfy a modified or different theory of gravity altogether. And from their emissions of Hawking radiation, gravitational waves, whatever, scalar waves, we could, just from the frequencies, infer, okay, what theory actually predicts the correct version? So assuming we would find a black hole emitting some weird frequency which would match, however, some predicted supersymmetric gravitational theory predicted frequency. So we have a theory which is complicated and predicts an alternative theory which predicts the correct frequencies of something we have measured. We could actually say, okay, fine, we found a test or a proof for something, or at least an evidence for supersymmetry to be correct. And so black holes are, for this reason, very interesting. And a second thing is, of course, why black holes are interesting is that the ADS-CFT correspondence proposes much more. Namely, well, we have to understand, if you will, other things also. Okay, why does a black hole emit Hawking radiation? This radiation which sets a temperature of the black hole and emits its information again out. Or radiates a lot of its energy away over time. It's also, in a way, semi-classically derived, but also not properly understood. A second thing is, okay, where does the information go of a black hole? Quantum mechanically speaking, information is a conserved quantity. But black holes of 2 stars with the same mass, angular momentum, and charge are the same. All other features of the star vanish, which is a problem, because that would contradict that information is something which is conserved. And so ADS-CFT correspondence is in a way used again to understand, or holographic duality to understand, is information something which is existent? Is the information contained inside the black hole? Or better said, what it actually proposes is different. It says the information doesn't go inside the black hole, rather it is stored on the boundary of the black hole in forms of strongly coupled particles. So again, we have the boundary, which is something which has a CF conformal field theory on it, and we have the inside with the information, but we can understand the inside by just knowing the boundary, because the boundary is not inside the black hole, so we can actually, again, see maybe the boundary already has the information we need. And so if we perturb the boundary, I'll get to a second, maybe information is stored in the detected gravitational waves. And so that would again give us a test of GR. Another thing, of course, things like wormholes and everything like. And this information is called hair, so the hair of a black hole. And this is something which is then tested, is called the no-hair theorem, because in GR, classically speaking, it says a black hole is only defined by mass, charge, and angular momentum. In ADS-CFT, it says there are much more information, more hairs in black holes. Or even better said, black holes are containing much, much more information, much more defining properties that quantum mechanically need to be there because information can't just evaporate and be gone. But it has to be there, it has to be stored on the boundary. But we, so far, could not find it. Okay, and now I'll come to the end, which I also should. Gravitational waves, again, let's come full circle. How can we now use them properly? Well, we can understand them as, if you will, linear perturbations of these boundaries again. So if the information is really stored on the boundary, well, then, I mean, if you perturb the boundary, we hope that the emitted gravitational waves contain information about the hairs or the information of this black hole. So when we look at all of this, well, then actually this sounds very compelling because we can kind of understand in a way that the information contained inside a black hole, well, could be radiated away from gravitational waves or other sort. Now, so far, we can measure these waves, and surprise, surprise, nothing so far has contradicted this no-hair theorem, and so we're still in the blue there if this is really true. But what one has done so far, and that's something that's maybe to kind of give a more hopeful ending to this talk, is one has looked at scalar perturbations, not waves, but scalars. Just, you just change certain components of your metric, see what happens radially, for example. That is something which has actually been done, and one actually could show that the holographic duality actually predicts the correct modes, the correct frequencies scalarly. So in a scalar sense, for very simple black holes, one has done this for example, non-expanding, expanding black holes, rotating black holes, and one has found the frequencies more or less match, numerically speaking at least. And one other example that's been done so far is the so-called BTZ black hole, which is a three-dimensional or lower dimensional setting, which in a way gives us already evidence, because there one has shown not only the scalars, but also the tensorial the wave perturbations, that they match the classical predictions. So that is the more hopeful outlook, saying that GR in a way, and this holographic duality do propose a good theory of gravity. However, it remains to be shown whether really that's the case. And that's a very, very difficult thing to do. And I think, yes, that's why that's what we all hope for, maybe, or not. All right, that brings to the end. So I thank you for your time and your attention. And yeah, that's me. I'm done.
Yeah, so thanks, Rob, for the talk. I think it was very good. Give us a very down-to-earth introduction to something that seems very complicated. So now we go to the apéro, as we usually plan. It's in G69. Yeah, so come to the apéro. And we're back next week. I think next week we're talking about semi-classical analysis. So come back next week. All right.